Hello, today we're going to talk about the assessment of multiaxial fatigue of crankshafts subjected to both designed and theoretically critical loadings. Firstly, please let me introduce the main authors. My name is Thiago Castro, and I'm a PhD student of Material Science and Engineering at Pontifical Catholic University of Rio de Janeiro. The other main author is Lucas Araújo, and he's a PhD student of Mechanical Sciences at University of Brasília. Fatigue failures of motor crankshafts operating in thermoelectric power plants are recently being reported. Since crankshafts are subjected to non-trivial stress states throughout their operations, multiaxial fatigue theory is required to accurately assess the fatigue behavior of the mechanical components. Crankshafts are typically forged in 42 chrome molybdenum 4 and 34 chrome nickel molybdenum 6 steels, which are respectively similar in terms of mechanical properties to the 4140 and 4340 steels. A finite element analysis was carried out to determine the in-service stresses in 20 critical locations of the crankshafts throughout its cycle. The crankshafts present 10 main journals, each one of them with a couple of connecting rods. This adds up to 20 different critical locations in the main journals where the cracks were initiated. For each critical point, an Excel spreadsheet similar to the one presented was produced. The cycle itself requires 2 complete revolutions of the crankshaft, which can be discretized, considering steps of 1 degree, into 720 angular positions. On the right, we can see a plot of the bond misses and the principal stresses as function of the angular position of the crankshaft. Since it's not possible to experiment these complex loading conditions, it is important to establish a methodology to extract a normal stress history and a shear stress history that can be put to test. Here is an example of the stresses that can occur at the connecting rod B of the 10th main journal. The adopted criterion considered the variation of the maximum principal stress, thus yielding the normal stress amplitude and the normal mean stresses. As for the shear stress, one can obtain it by considering half of the difference between the maximum and the minimum principal stress. Since well-established experiments reveal that the presence of a mean shear stress does not affect the fatigue life of a mechanical component when subjected to a very high cycle fatigue regime, and considering the fact that the design stresses are to be kept low enough to maintain the crankshaft within the elastic regime, it was decided to consider the maximum obtained value for shear and consider it equal to the shear stress amplitude. By choosing the loading conditions that yielded the greatest von Mises equivalent stress values, the finite element method extracted loading conditions can be summarized into the 6 presented, in which 3 of them are in phase and the other 3 are out of phase. As one could expect, the loading conditions are rather low, and the specimens subjected to such loading conditions could be expected to present a runout. Therefore, it was decided to generate an additional couple of loading conditions that could be, within the same methodology, slightly more aggressive to the specimens. The greatest in-phase and the greatest out-of-phase loading conditions were selected, and by considering the amplitudes equal to the maximum stress values, this gives origin to a couple of fully reversed loading conditions with a much greater stress amplitude. As one can observe, the new stress amplitudes correspond to the summation of the previous stress amplitudes to the previous mean stresses. The apostrophe next to each one of the loading conditions' name is to indicate the presence of a mean normal stress. The selected loading conditions to begin the experiment are pointed out with the right arrow. 2 specimens were carried out for each one of the selected loading conditions. All of them managed to endure 10 million cycles without failure. So, referring to the literature, Papadopoulos presented a list of loading conditions to a set of different steels that are theoretically critical. This means that the presented stress values corresponds to the limiting state of non-fracture of the specimen for a number of load cycles of the order of 1 million. As it may be observed in Table 1, one of the materials listed is exactly the 42 chromolybdenium 4 steel considered in the present study. Since we have already experimented with this material, a previous work of this research group has experimentally determined the uniaxial fatigue resistance limits for both normal and shear stresses. These values of fatigue resistance limits will from now on be considered. Unfortunately, when subjecting the specimens to these loading conditions, we experienced many unacceptable failures, such as the one illustrated on the bottom right corner. Due to this fact, we managed to have only 2 acceptable values, 3 runouts, and 7 unacceptable failures. These unacceptable failures happened because the pressure of the collet to hold the specimen in place was too high. The collet's pressure over the specimen is evaluated as a function of the applied loads. So in order to reduce the grip pressure, we updated the geometry to a thinner cross-section, which allowed to maintain the stress levels while reducing the loads. This geometry was chosen because we had previously used it before, and therefore we had already the adequate SN curves already determined. Although the experiments with the new geometry are still being carried out, a theoretical analysis is still very effective. All multiaxial fatigue criteria are similar in terms of its application. The left-hand side of the expression is usually associated with the applied stresses, and therefore is associated to the driving force to failure. The right-hand side, however, is associated with the fatigue resistance limit. When the left-hand side equals the right-hand side, the criterion is indicating a limiting state of non-fracture. This means that one could use the proposed loading conditions presented by Papadopoulos and expect to obtain the critical situation where left-hand side equals the right-hand side. However, in Papadopoulos' work, the fatigue resistance limits were different than the ones that we observed in laboratory. This means that we can further verify the models because once we input the given stresses, the left-hand side and the right-hand side are most likely to differ one from another. It is important to point out that a negative error index means that the driving force to failure is less than the resistance limit, and therefore the criterion indicates that the material should resist. On the other hand, positive values of error index indicate that the material is expected to fail, and therefore this indicates a conservative behavior of the criterion. So if we take, for example, Carpentier and Spagnoli's equation, you can see that Nmax and Ca are associated to the stresses acting on the critical plane, while F-1 and T-1 are fatigue resistance limits in both normal and shear conditions. So if the left-hand side is greater than the right-hand side, if you look at the equation that is associated with I, this numerator is going to be positive. And once that happens, it means that the criterion is indicating failure. Alternatively, if the right-hand side is greater than the left-hand side, this will give a negative error index, and this indicates that the material should resist. The bar graphs indicate an average value of the obtained error indices to each one of the loading conditions. The considered criteria were Mataki, Findley, McDiarmid, Carpentier and Spagnoli, modified Carpentier and Spagnoli, Liu and Mahadevan, Papadopoulos, and Susmel and Lazarine. As one could expect, all loading conditions extracted from finite element analysis, despite being fully reversed or in the presence of mean normal stresses, all the obtained error indices are very negative. This indicates that the crankshafts are not subjected to inadequate loadings, and the reported failures are very much likely to be a consequence of metallurgical aspects. As for the critical conditions presented by Papadopoulos, the considered criteria yielded averages within the plus or minus 13% range. It is important to point out that, except for the loading condition B, all the averages are either very close to nil or are positive. In fact, there are more positive values than negative values, and the overall average is positive. This means that the criteria, in an overall manner, are relatively conservative, which explains the 3 runouts we experienced. The runout number of cycles, by the way, is 10 million cycles. So if we were to fail in the order of 1 million cycles, and we did experiment 10 million cycles without failure, that must mean that the criteria are slightly conservative, or rather conservative. And that is what we can see, because we get positive values of error indices, indicating that the criteria should present a failure, but it does not. All of this leads to the following conclusions. We have managed to develop a methodology that could report a non-trivial stress state to a combined normal and shear stress amplitudes. That could be put to test. Finite element method extracted loading conditions were low, leading to infinite fatigue lives. Runouts were no surprise. An additional set of loading conditions was considered. These loading conditions are expected to lead the material to a critical condition on the verge of failure. Unfortunately, experimental problems arise which imposed updating the specimen's geometry to reduce the grip's pressure, avoiding the out-of-place failures. Despite not having all the desired experimental results, a theoretical analysis is still very effective. The finite element method loading conditions yielded error indices that are very negative, meaning that the crankshafts do not fail as a consequence of inadequate loading conditions in operation. The other set of loading conditions, considering real fatigue resistance limits, yielded average error indices close to nil, but still indicated that the models tend to be slightly conservative. This research was developed within the scope of the Research and Technological Development of the Brazilian Electric Energy Sector Program, regulated by ANEEL, with the support of the Eneva companies PECEM2 Energy Generation SA, Itaqui Energy Generation SA, Parnaíba Energy Generation and Commercialization SA, and Parnaíba 2 Energy Generation SA. So I hope you have enjoyed. I thank you very much for your presence, and these were the literature references that were considered to this work. Thank you very much. I'll be happy to answer any questions that you may have. Please feel free to ask. Thank you very much. Kind regards. Bye bye.